This is Morgan here with Positive Approach to Math. We are moving right along in our Algebra 1 topic. We're moving on to linear equations. So linear equations are a big part and kind of one of the main things I would say that you cover in Algebra 1. So this is our fourth topic. There are 9 lessons that are in this category. They are very broken down. So a lot of these in your class you probably do more than one of them in a day, but we wanted to be able to make sure that your lessons are nice and short for the videos, so they are very much broken down one skill at a time. So this first lesson we have here is talking about what is a linear function. What does it mean to be linear? And I like to always point out to my students that the word linear has another word in it, and that word is line. And if you can remember that, that's what a linear function is. It is a straight line. But it's more than a straight line. What does a straight line consist of? And you can go down all of these avenues, but talking about the heart and soul of it, a linear function is representing two quantities. Typically, we use x and y, an input x, an output y, and that when you graph to represent the relationship of those two quantities, the graph shows a straight line, meaning that the rate of change is constant, okay? If you go to graph two quantities and it does not turn out to be a straight line, say you have a bunch of ordered pairs, and when you plot all of them, it is not a straight line, then it is a non-linear function, okay? But here's the thing. We know that for something to be a linear function, it derives from a linear equation. So when we can look, we don't have to graph everything to determine, we don't have to make a table and say, okay, let's pick some inputs, let's find their outputs, let's plot. Okay, linear, nonlinear. We don't have to do that every single time. We can learn and understand and recognize some patterns from linear equations that makes our life a little easier, that we can look at that linear equation and say, based off of this, we can determine that yes, this would represent a linear function, or no, it would not represent a linear function. So rather than having to graph every single thing, we want to recognize some patterns that will differentiate linear to nonlinear. So if we have a linear equation, that is an equation that will have two variables in it, most typically x and y, have at most two unique variables, okay? So it could potentially have just one, right? But there's going to be something special about that one variable that it has that we're going to talk about in this next thing. Step 2 says our variables must have an exponent of 1, and that's what I was kind of getting at there. So you could have all of an x or all of a y, but you can't have something with a y squared or with an x squared, right? All of the variables must have an exponent of 1. And typically, we don't write x to the first. We just write x. So we don't write y to the first. We just write y. So you will see something with an x and a y, at most two variables, but both of those variables will have the exponent of 1. And that is one of your quick, easy ways to see, okay, is this a linear function? You see an x squared, or you see a y to the third, or even like an x to the 1/2, something like that. Automatically nonlinear, okay? Our next rule is that all of our coefficients and our constants must be real numbers. So remember, to be a real number, we do not have any negatives under our square roots. So it can be a fraction or a decimal, but it has to just be a real number coefficient. Remember, coefficient is the number in front of your variables, or a constant. A constant is a number hanging out on its own with no variable attached. And the last kind of trick I look at is that something that would represent a linear function has no variables in the denominator, meaning you might see this 1/2 times x just because there's a fraction, that's okay, but you won't see this 1 over 2x. So when that variable goes in the denominator like that, that's a major, major no-no, automatically nonlinear. So you could have a fraction as a coefficient, but that x or that y would not be in the denominator with that fraction. Okay, so this is very straightforward. Looking here, we have 6 equations, A through F. We are going to determine whether they are linear or nonlinear. And rather than write linear, nonlinear, we're just going to put them in their boxes. I'm going to talk about for each one what makes it linear or what makes it nonlinear. So looking at that first equation A, we have 3/4 x plus y equals 2. So I look at my variables right away, x and y. First of all, they both have an exponent of 1. That is great. They don't have anything crazy. I say, is anything crazy happening to them? That's what I normally say to my students. And what I mean by crazy is, is there anything that is an exponent other than 1? I mean, is the x or y under a square root typically? And, or is the x and y in the denominator? That's what we're looking for. Is there anything crazy happening? And there is not, right? So it's just a plain, I say if it's a plain old x and a plain old y, we're in the clear. So we are in the clear there. And then I say, okay, 3/4, real number, 2, real number. And technically the coefficient in front of y is a 1, which is a real number. So A would be a linear equation. So there, if you had to graph it, you would have a nice straight line. Letter B. We have y equals 4x squared minus 9. Right away, we do see our two variables, which is great, but I see something quote-unquote crazy happening to that x. It's being raised to the second power. So, oopsie, I don't want that. So once you see that exponent, that tells you this is not a linear equation, so that would classify as nonlinear. Whoa, that's a weird B. Nonlinear, because it has an exponent other than 1 on one of the variables. Okay, letter C. We have 3x plus 4y equals 2z. Right away, I recognize that that is nonlinear because you have a third variable. So you can at most have only 2 variables. Now, granted, all of those variables are just a plain old x, a plain old y, a plain old z, but you cannot have more than 2. So we'd have to get rid of one of them. Okay, letter D, y equals -2/3 x. So nothing crazy happening to that y, nothing crazy happening to that x. -2/3 is a real number, so that would be linear. What I would say here is sometimes students will say, well, there's no constant. That's okay. It doesn't say to be linear you need a constant. You just need at most 2 variables, nothing crazy happening to those 2 variables, all real numbers, and then you're good. Okay? Letter E, try to trick you here. 2x plus 4y minus x equals 3. So we want you to say, oh, there's more than 2 variables. This would be nonlinear. But that's not the case. Notice you have like terms here. Whoa. You have a 2x minus 1x. Those are like terms. We can push them together. We can simplify before we go to evaluate this. So 2x minus 1x would just simplify to 1x. The 4y would stay equals 3. So now when we look at this, we have just an x, just a y, nothing crazy happening to either of those, right? So we know, okay, great, this will be a linear equation. Cool. And last but not least, letter F, we have 3 over x plus 2 over y equals 1. Right off the bat, hopefully you see, okay, well, we have a fraction and those variables are in the denominator of the fraction. If they were in the numerator, no big deal, but they cannot be in the denominator. That makes it rational, something you're going to learn about way, way, way beyond this course in your math journey. So that would make this a nonlinear. Now, one thing I want to point out is if only one of those were in the denominator, like the x or the y, and the other wasn't, it would still be nonlinear. Both of them have to just be plain old x, plain old y. Neither could be in the denominator. So we had 3 that were linear and 3 that were nonlinear. So as we wrap this up, just a little summary here. Linear functions are functions that change at a constant rate. And that constant rate, that constant change, is what makes that a nice straight line. You're saying, okay, as I change in y, my change in x, and it stays the same. And that's what forms that nice straight line through all of those points, which we're going to see in a little bit. We can always determine whether an equation is linear or nonlinear without having to graph it, looking at certain criteria. So remembering that there has to be nothing fancy happening to your x. It has to be a plain old x, a plain old y. You can't have more than two unique variables. And it can't be in the denominator, can't be under square root, can't have a crazy exponent. And your constants and coefficients must be real numbers. Once you have a linear equation, you can use that to graph a linear function, and it should come out as a nice straight line. Okay? So I left you with 6 problems here, really easy peasy. Determine whether or not they are linear or nonlinear. So why don't you give those 6 problems a try? You can click on the link in the details for the video if you need some help talking through those 6 U-tries. You can also click on an answer key if you just want to check your work. Remember, everything you need is in the details below, a blank PDF of these notes for you to fill out, either on a tablet or to print, as is those videos and answer keys to the U-try. Great job with our first lesson to linear equations. I look forward to continuing this topic with all of you. Keep up the great work.